Hello, everyone, and welcome to this 13th episode of Passages, a scientific podcast presented by Amundsen Science and recorded on board the CCGS Amundsen. My name is Véronique Rochefort. I am the communication manager at Amundsen Science. I'll be your host for today's episode. Today, I'm joined by Dr. Jay Cullen, director and professor at the University of Victoria. Right now, we are in Saguenay's Fjord, Quebec, for the sea trials, preparing the research vessel to leave for 114 days of science at sea. So hello, Jay.
Hello.
How are you today?
I'm well. Thank you for talking to me today on episode Lucky 13.
Yeah, we're so happy to have you at Passages. It's the first time for you, huh?
It is.
Yeah. It is the second episode of the second season, so we're starting slow. We're doing this special episode just with you, Jay, for the first time. It's just with one guest. So really happy to have you here.
I'm the guinea pig.
Yeah, exactly. We'll be able to test if this format works.
Mm-hmm.
Are you happy to be here on the ship for the sea trials?
I am. Sea trials are really exciting. You get to see what other teams are planning for the coming field season. People are testing new gear, new ideas. There's some uncertainty. People are wondering if things are going to work, and everyone's working really hard and working together to get prepared for the summer.
Yeah, and as I did my research, you have a lot of area of expertise. I saw that you're a chemical oceanographer, marine biochemistry, bioinorganic chemistry. It's a lot.
It's a lot. It's all related to answering very similar questions, however. So it ties together my background in various areas of biology and chemistry.
Yeah, can you explain a little bit more about what is your main research interest?
My main research interests are in the area of trace elements and isotopes. So these are chemicals, elements that are found in the marine environment that give us a lot of information about how the ocean works. So both physically how the ocean circulates and mixes. It gives us information about rates and dates. So some of the isotopes are really useful for example, finding out how much material is sinking from the ocean surface into the interior. And they also give us information, or they're important for marine microbes. So phytoplankton that are the base of the food web need certain elements for their nutrition, just as you and I do, in order to grow and to be successful. And because that leads to the movement of things like carbon dioxide from the atmosphere and how it's stored in the ocean on really long time scales. We're trying to understand how trace elements, metals like iron, for example, might affect how the oceans either modulate climate change or how they're involved in the movement of carbon from the atmosphere into the ocean, which affects the long-term climate of the planet. So there's sort of short-term questions and longer-term questions that we can address with trace elements and isotopes.
Yeah, and so we're talking about really tiny particles that we cannot see with our eyes.
That's right. So, and we're also talking about really large space and time scales. So, making measurements or estimating, for example, how much organic matter that's made by the phytoplankton, how much sinks from the surface of the ocean to the deep ocean. That's a really difficult question to answer. And these trace elements and isotopes can integrate those time and space scales to give us a clear picture about how much the oceans, for example, are sequestering carbon dioxide that we're releasing to the atmosphere through human activities. How much of that actually ends up in the ocean? Those are the sort of big questions that the kind of work I do and my group does contributes to trying to answer.
Yeah, and so that's why you're covering a lot of area of expertise, because it's so connected to a lot of various phenomenon.
Yeah. I think one of the ways to explain it is that the ocean and how the ocean carbon cycle works, for example. It's very complicated. It involves understanding the growth rate and the growth requirements of these microscopic organisms. So both photosynthetic organisms, that plants of the ocean, and also bacteria, for example, we need to understand how they grow, what limits where they grow, and what types grow in different places, because ultimately that sets how productive the ocean is in terms of our fisheries, but it also affects these fluxes of materials from the atmosphere into the ocean. And that involves understanding the chemistry, the biology, the ecology, the physiology. So that's how it all ties together. So, I don't know all of those things, but I collaborate with different groups and different colleagues who understand, the physiology, colleagues who measure different aspects of the chemistry that my group doesn't. And so it's a very collaborative and multidisciplinary set of problems that we work on. And one of the reasons why we do work with the Amundsen Science to go to the Arctic to try and answer some of these questions.
Yeah, and I'm sure you have to keep updated, and you have to study and continue to read a lot of scientific paper in order to be updated. Yeah.
Yeah, to stay on top of everything that everyone is doing is almost an impossible challenge. But as you're answering these questions, you do need to learn a lot of new things. So that's one of the attractions of being a professor, a research professor who's working on these sorts of problems, is that you're challenged to continually learn new things, and you're always working and teaching and working with young scientists, and that's also very rewarding because one, you're constantly around young people, and you see how and what people are thinking about and their approach to problems. But it's a continual challenge. You're always being challenged with new approaches, new methods, new ideas, and I think that's healthy overall.
Yeah.
And fun. Yeah.
Yeah, you're like an eternal student.
Certainly, my parents seem to look at me that way. I've never really left school, and most of us who are here doing this kind of work never really do. Yeah.
What did you study first at school?
So once I left high school and started university, I was interested in studying biology and or chemistry. I wasn't quite so sure. So I went to McGill University, and I was in Montreal, and I wasn't quite sure whether or not I would go into medicine. I thought maybe perhaps I would practice medicine because I'd always been interested in helping people, and I was interested in biology. But when I was at McGill, I started working in a laboratory. Professor Neil Price, who is working at McGill still today, and his laboratory was designed to understand the trace metal requirements for the physiology of marine microbes. And I started working there. I was really fascinated with the problem because, the approaches were the research itself was very interesting, but thinking about the ocean and thinking about how important it was to life on the planet broadly, it was a very attractive field of study. And he was a very great teacher and a very great mentor. And the research group that was there was very exciting. And I became very interested in the oceans. I'd always been interested in the ocean since I was a child, but being able to study it was new and exciting. And it was then that I decided that I wanted to be a research scientist and that I was quite interested in the oceans. So from there, I started doing a PhD at Rutgers University, which is in New Jersey in the United States. So I moved from Montreal to New Jersey. And I was finding myself more interested in the analytical chemistry of measuring these metals at very low concentrations in the environment. And some of these metals are nutrients that help living organisms, but some of them can be toxic. So metals like lead, for example, or some radioactive elements in the marine environment can harm things. And so understanding where those elements come from and where they go in the marine environment was interesting from my perspective. And learning the chemical techniques to make these very low measurements appealed to the chemist in me. So that's where my training went for my PhD. And then I moved to Woods Hole Oceanographic in Massachusetts on Cape Cod to do my postdoctoral work before finally ending up on the West Coast in Victoria, where I've been for the last 22 years now.
Yeah. Mm-hmm. And did you grow up in Montreal?
No, I didn't. I grew up in central Ontario. So I grew up in a city called Peterborough. which is in the Kawartha Lakes area. So growing up, I was always around water and always really interested in swamps and lakes and fishing, and always fascinated by living things in the water. And I think from a very young age, I was always reading books about the ocean and adventure and exploration. And so water, science, adventure, exploration, those were always things that were front of mind for me, and something that drove, what I wanted to be when I grew up.
So it was an interest, but you wasn't thinking about doing things with water for a job when you were a kid.
No. When I was a kid, and even when I was in high school, like a lot of people, I think it wasn't clear to me what I wanted to do or what path one would take to have a career in science or medicine or whatever the case might be. It was just what I found most interesting, and I think that I was, or I have been, quite lucky to be able to combine those interests and things that drive my curiosity with my job. So I consider myself quite lucky in that respect.
Yeah, being a marine researcher, I think it's a field that is unknown when you're kids. So these kind of jobs are not really in our head when you were taking like medicine or being a veterinary. It's more of the job that we know about and we aspire to be. But I think it's nice to like follow a path and be inspired while you study and just choosing.
Yeah, exactly. I think, growing up, I didn't see the ocean until I was 11 or 12 years old. And certainly you didn't meet oceanographers or marine scientists except in books, reading about like Jacques Cousteau or other famous oceanographers. So you don't meet people doing this sort of work. Certainly Canada is such a large country, and most people aren't growing up on the ocean and seeing the ocean every day or meeting oceanographers. So I think that I was just drawn to it over time. And when I did realize that it was a way that I could learn about the planet, and I could do it for a living, do it for my career, for my job, it was exciting. And I've never regretted, taking the path.
There was no time when you were thinking about doing something else?
Well, I mentioned medicine early on. My mother was a nurse before she retired. I have to say she actively discouraged me from being a doctor. She felt that medical doctors...
the schedules are not really open.
and it's a challenging life in a lot of respects. But I had dreams of being like any young child. I had dreams of being a firefighter or a hockey player, obviously.
An astronaut, maybe.
An astronaut, maybe. That one never really left me. This idea of being an explorer or taking on a challenging job was always something I think that I aspired to.
Yeah, let's jump through to what you're doing here on the research vessel. So you said that you look for a trace element. You're using the trace metal rosette. Can you explain what it is and what is doing the trace metal rosette?
Yeah, so the one of the largest challenges of this work, outside of the analytical challenges back in the laboratory of making measurements of these metals, they're in very, very low concentrations in the environment, but in the built environment, around buildings or on a very large research ship like the Amundsen, the metals are quite abundant. The ship's made of steel, iron, there's electronics, there's oil, there's grease, and all of these are very, very high in trace elements concentrations. And so collecting a seawater sample that's uncontaminated by our handling of it or its proximity to the ship, that's a really big challenge. And so the trace metal rosette is designed to return seawater to the ship completely uncontaminated with metals like iron and zinc that are really abundant, in the built environment, is what we say. And so it's made in a way that's a little bit different than the regular rosette, the regular ship's rosette. We try and eliminate any metal parts on the rosette so that when we dip it in the ocean, it doesn't act like sort of like a tea bag that's releasing metal to the seawater around it. So we replace all the metal that we can. We have special sampling bottles that are lined with Teflon, which is very good or we can keep very metal clean. And instead of having a metal cable that goes over and puts the whole trace metal rosette into the water, rather than metal, it's a synthetic sea cable, which is not common to see. And we go to great lengths to keep the seawater as clean as we can. So what we're measuring reflects what's in the environment rather than what's in the materials that we use to collect the sample. Mm-hmm.
And what are the difference in the bottles for the TM rosette and the classic rosette?
Well, the classic rosette, the way that the sampler works, if the listeners can imagine, it's sort of like a long tube that closes on both ends. It goes over open, and then when you're at a depth in the ocean that you want to collect the seawater from, you tell the bottle to close. And the way the classic ship's rosette bottles work, they have a spring, an elastic that runs right down the center of the bottle that connects the two ends, the caps of the tube. And that elastic pulls the bottle closed. And the seawater inside is in contact with that elastic, and that can contaminate with metal. Our bottles have the elastic on the outside of the tube. And the insides of the tube are coated with plastic, Teflon that prevents metals from sticking to the walls and sort of seeping out and contaminating our seawater sample. So, the bottles are designed a little bit differently. And again, every attempt is made to prevent or to use materials that are very pure and clean with respect to metals.
And we are deploying the TM rosette in a moon pool here on a ship. So it's a hole in the hull of the ship.
Mm-hmm.
Is it a place where you choose to do it, or is it more like an operational decision?
It's a bit of both. So historically, we would work on the starboard side of the bow of the ship and use a crane to put the trace metal rosette over and the winch to play out the cable to put the rosette down into the water. But the ROV, the Astrid, that the Amundsen operates, it used to go through the moon pool, but it's been redesigned and it's bigger. And so it's being deployed from the deck. And that gave us the opportunity to move the trace metal rosette down into the moon pool. And there are advantages. There's a few important and few sort of comfort-related advantages to being down in the moon pool. One is that in heavy sea ice, when the ship is breaking ice, one of the dangers of operating the rosette from the deck of the ship is that there's sea ice around, and it can cut the cable and it can cause a lot of problems. Whereas the moon pool is in the bottom of the ship, and we can directly deploy the rosette without worrying about ice at the surface on the sides of the ship. It's also comfortable. Being on the deck in the Arctic, as you know, Veronique, can be uncomfortable. It can be very cold. It can be raining. It can be very windy. You're always wearing a Mustang suit to try and stay warm. Your feet, your boots get very cold on the deck, standing for hours as you sample. In the moon pool, we're out of the weather. You can work in your shirt sleeves. And you've got a lot more control of the area around you. So it's easy for us to move our samples from the rosette into the trace metal clean lab. I can talk a little bit about that, but it's just a very comfortable, controlled environment, and that's exactly what you need when you want to collect samples where you minimize this environmental contamination. We can really control things down there, And it's a really unique way to collect these sorts of samples. The Amundsen Science has really supported us to develop this tool, this facility to measure trace elements and isotopes in the Arctic.
Is there any challenge in putting the rosette through the moon pool that is all covered with metal?
There is. So we try and minimize the opportunity for the samples to be contaminated with the hull of the ship. When we go off the side of the ship, we're still really quite close to the hull. The moon pool is a little bit more daunting when we look at it because it's surrounded on all sides by the hull of the ship. We try and get the rosette down through the moon pool below the hull of the ship. We know from past experience of sampling through the moon pool that we're not contaminating the samples, but it is challenging, and there are certain additional steps of deployment that we have to take that we wouldn't normally take on the deck of the ship that make the deployment a little bit more challenging. And that's one of the reasons why we're here at Sea Trials, is to test new mechanisms, new equipment for the deployment of this rosette.
And so since last year, you have now your own space, and you also have your own clean lab. Were you involved in the construction of the clean lab?
Yeah, we worked with the team here with Amundsen Science to design the facility. So what historically we've done on the ship is, one of the controls that we have to have on the environment to collect these samples cleanly is that we have to make sure that particles in the air, metals that are coming from the ship don't settle into the samples or otherwise contaminate the sample as we're working with them. And we would build a structure sort of like a homemade greenhouse, where we would build a wood frame and use heavy plastic to enclose the space, and then we would blow particle-free air in, filtered air into the space, and work in there. And it works. However, what was decided is that we would use a part of the moon pool to construct a clean lab. And these are labs where all the interior surfaces are made of plastic. The flow hood, there's filtered air that's being pushed over the area where we're working with the samples, so there isn't a potential to contaminate them. And the entire facility is positively pressured relative to the ship, so that air is only flowing out of the lab and never in. And all the air that's being pushed into the lab is also particle free. It's filtered to submicron sizes. So it's very clean air, and it's a very clean space. And so designing that and having it built, it was really fantastic to have the support of Amundsen Science to install this facility. And so working with Luc Michaud, who's now, not unfortunately for him, but retired, Simon Morissette, and other members of the technical team, it took a lot of time, but it was designed very well, and it was constructed very well. And so now we have this ability to return the seawater with the trace element rosette in this controlled environment, and then immediately move into this clean laboratory. It's a really unique facility that's housed in the belly of the ship, and allows us to do really great work.
And you had the opportunity to test it last year. Mm-hmm. Was it good? Did you have to make some improvements?
Well, there were subtle improvements. We're always going to be improving it. But last summer was the first opportunity for us to use both the rosette through the moon pool and the clean lab facility. And we're just making measurements on those samples that we collected last August in Nares Strait as part of the Refuge Arctic program. And the samples look great. We're excited about the way the data works. Over the winter, there were improvements made to the guide that's used to make sure that the cable doesn't contact the side of the ship and potentially cut the cable, so that we would lose the trace element rosette. We're testing that here on Sea Trials. Yeah. Inside the laboratory, we've installed some drains that make it easy for us to get rid of seawater that we don't use inside. There are racks inside the clean lab where we put our sampling bottles. They're 10-liter volume bottles, so they're quite heavy, and they rack so that we can sample them cleanly and easily inside. And so the team continues to work with us to make things better so that our scientific objectives can be met, but also somewhat more comfortable and less hazardous. Carrying these large sample bottles around can be dangerous. It's one of the things that we're always thinking about is safety. And so, yeah, things continue to get better, and we're testing them and quite happy with the way things are working.
And it's the main reason why you are here on the sea trials, is to test an improvement of this deployment.
Mm-hmm. Yeah. So over the winter, as I mentioned, Simon Morissette, we were talking about ways to improve this guide for the cable, and it's difficult to describe, I think, on the radio. But effectively, what has to happen is that the cable has to be prevented from hitting the side of the ship when the ship drifts with the wind, or if there are strong currents. And last year, what problems we had when we were working through the moon pool were related to this cable guide, and it's been improved. But it was untested, and so over the last few days, we've been making the first deployments with this new equipment, and it's performing really quite well. And again, it shows how science in general, whether it's the questions you're asking or the equipment that you're using, is continually improving, and it's collaborative. So, we use it. We say, "Oh, this isn't so great." The ship's crew weighs in. This would be better if we did it this way. And then the Amundsen science team takes that away and designs and comes back with something different and new. And so far I have to say we're really pleased with the way the new operation is working these last few days.
And I think from our part in Amundsen Science, I think this is kind of projects that we really like to do because we work with you, and we can see also if the improvement is working, if you like it. So it's always rewarding for us to work on something like that.
Yeah. Mm-hmm.
And I think this is going to be my last question for you, but
okay. Mm-hmm.
Maybe the most important one. Yeah. I am wondering why you choose the Amundsen to conduct your research project.
Well, there's a number of different reasons, but the main reason is that I think that as a scientist and a Canadian, I'm really focused on what's happening in the north, and as you know, the Arctic is changing very rapidly. So regional warming is happening in the Arctic much faster than it is happening anywhere else on the planet in response to anthropogenic climate change. And how that warming is going to affect the Arctic has a lot of implications for Canada, with respect to our sovereignty, with respect to our responsibility to be stewards for our environment in this massive country that we're responsible for. And the Amundsen is a great platform for accessing the Arctic and for asking questions about the marine environment. It's a unique combination of a very skilled crew from the Canadian Coast Guard, a very capable vessel, so ice strengthened and ice breaking, and experience of working in the Arctic, and then Amundsen Science, that technical support and an understanding of what the scientific goals are, working very closely with scientists from all across the country, and not just within Canada, but internationally as well. So that's a unique combination that allows us access to this environment that's rapidly changing, and that is really important for us to understand what those changes mean for us.
Yeah. Okay. Good. Thank you so much. Thank you for being with us. So this was the 13th episode of Passages. 13. Yes, exactly. Thank you for being here, Jay, and thank you for everyone that listened to this episode. It was the first time we have just one guest at Passages, so we hope that you really liked it, and do not forget to follow us on Instagram, LinkedIn, Facebook, and Spotify. Thank you, everyone, and see you at the next episode of Passages.